I would now like to hand over to Mr. Rubin de Cervens. He is director of the French Marine Accident Investigation Board. And so you are familiar with incidents and accidents having occurred involving French vessels worldwide. So the BEA Mer is very well known for the great accuracy of its information on each incident that occurs. So over to you.
Yes, good morning, sir. Good morning, everyone. It's a pleasure to be with you here today. And I'd like to begin my presentation on the subject. There we are. Perhaps you can see my presentation. Perhaps the English conference room cannot yet. We'll see. So, of course, we're going to talk about this from the point of view of the French Marine Casualties Investigation Board. I'll more specifically talk about, in this very simplified version, parametric rolling, and explain how this develops aboard a vessel. And I will conclude with some avenues for the future, avenues of improvement that we can glean from the various reports that have been filed. So, to begin, of course, it's fundamental to understand ship motion in the case of a casualty investigation, accident or incident investigation, and we see a direct link. In fact, if you look at this list of reports in this table, there are a number of containers lost, and we can connect this with the roll, the degree of roll. You have very broad motions of the vessel. In an accident in 2006, where we had a sea report, there was an accident where the roll was 20 degrees, another 30 degrees, a third, the Annabella in 2007 in Baltic, 30 degrees, roll, Pacific Adventurer in 2009, 40 degrees, the Svenborg Maersk in 2014, 41, the DMAIB, the Danish Accident Investigation Board, provided that information. And then in 2018, we had both the CMA-CGM in the North Pacific and the Yang Ming efficiency in Australia, respectively showing 20 degrees, 30 degrees, and finally in 2019, the MSC Zoe with 30 degrees of roll that created this accident, and the report was made by BSU, DSB, and the Panama Maritime Safety Board Authority, Maritime Authority. So here we have, in particular, you have the hull of the vessel to begin with. The hull, in fact, is going to determine a number of elements like stability, the number of containers which can be taken on board, and the behavior, plus the motor power, etc. So that, in fact, is predetermined, so to speak, for a given vessel. But before taking to sea, you have the loading, and this is very important. This will have a very important effect on the behavior of the vessel and the motor behavior. And then, of course, you have the heading and speed once at sea. So if you look at these aspects, the hull, the loading, the heading, and the speed, this creates a sort of block that is fairly well mastered overall by people. And you can use these elements to ensure that everything goes well when stuffing or loading or taking the sea. On the other hand, what we cannot control is the sea state. And in fact, the combination of all of these elements, the heading, the speed, the loading, and the sea state is going to determine, the loading in the sea state is going to determine how this vessel will move, with a number of movements in all directions. And of course, you're going to have rotating, you have sway, where you have the boat moving forward or moving back. Alternatively, pitch, back and forth, yaw, which is moving around the transversal axis, and heave, etc. So these movements all make for a very uncomfortable voyage. And there are a number of you who have already felt these sensations, not very pleasant, and they also have an effect on the ship's structure. So in the case of vessels that are very long in particular, you have a sort of suppleness, flexibility of the structure which is created and plays on the hull. Now, of course, this has an effect as well on the stacks of containers. And you can see the photo or the diagram on the right, where you have, in fact, settling or upheaval or the lashing load, which is important. And you're going to have a stack of containers that is going to rise, fall, settle. And I'm afraid I'm moving a bit too quickly. But so what's going to be important is when the lashing and the structure are not appropriately paired, so to speak. You have a number of rules that have to be mastered and controlled, and you have a number of rules on how solid and sound the containers themselves are. If we look at the phenomena that can come into play for the vessel, the dangerous movements can come from a following sea or from an oblique or quartering sea. So you, in fact, are going to have a form of acceleration that means that the ship is going to ride on the crest of the wave. And in those cases, the risk is that it will ride the trough or fall into the trough as it crosses. And this can lead to a very sharp change in the heading. And you can see this fairly often when a vessel is broached from behind. So you have a lower intact state stability when these waves touch amidship. And this, depending on the form of the hull, you can have this becoming a critical problem from 0.6 wavelengths that go from 0.6 to 3 times by 3 times the length of the vessel. So we have synchronous rolling. And this is the case when the natural roll of the vessel coincides with the roll of the sea. But when you have a quartering sea or an oblique sea, this is changed when you have a parametric rolling, when the natural roll is not in phase with the roll produced by the sea. So basically, on the next diagram, you see what happens when the ship rolls. You have a little drawing. In fact, the source of this diagram is Bureau Veritas. And you have the situation when the vessel is either in the trough or on the crest of the wave. You can have waves that can come and create significant roll. So here we have a situation in the trough. The stability appears and is actually increased. You have a bit of heel. And listing, and you have a sort of pushback from the sea. You have the ship which is leaning to one side, which is listing, and then this pushback will push it back to its original position. When the wave comes from its right, what we see on the right of this slide, you have lower stability, and it's not going to slow down the movement of the vessel, so the vessel will carry on with this motion with an even greater heeling or listing. Then when it comes back in the trough of the wave, the stability will be increased again, and this pushback will come from the other side, and this cycle is repeated. Oops. You see the water line depending on where the vessel is, either on the crest of the wave or in the trough of the wave. And you have very broad, violent movements of the vessel. If this is combined with the wave phase as well, you see the moment of the phase of the wave is indicated in blue here, and then the roll, which will appear, and will have this combination which increases the amplitude of the roll. Now, there are a number of parameters to be taken into account, and particularly the fact that when you lose rolling, it's during a half period, and that sort of calculation, but you can see that this makes for very sharp, brutal movements. Now, when we look at this phenomenon, the Maritime Research Institute, which has created mock-ups and models to measure the parametric roll. We're going to have an example by video. We see on the French screen, at least, we see a model ship moving forward. The captain instinctively would say, everything's going well, there are no major difficulties encountered here. It pitches significantly, though. But you could still think that the route is correct. If you were on board, you could consider that everything is still going well. But little by little, due to the parametric rolling, things are going to get more complicated. I'm sorry, we still have this video of the model tank, the ship in the tank. So you can see that if the effect changes even slightly, the ship can start rolling. We see it rolling increasingly from side to side. The motion is really getting stronger. And this is what comes into play, forces coming into play on the containers themselves. You have the effect on the movement of the containers and on the lashing, which could be more or less significant. When we have greater roll, the movements are even more significant. The forces is as well. Okay, we're going to stop this short video. So the question is, then if we look at the effect of developments in the shapes and sizes of container ships, and we're talking about going up to 24,000 containers. In the beginning, we only had a few container plans, and it's up to 11 now on a given vessel. So it's kind of like a metronome. The top of the arrow, the tip of the metronome moves faster at the top. We have changes in the size of these vessels and development in the shapes of these vessels. In the past, the stern had fairly sharp angles, 30 degrees, and now they are broader, more open angles that can be greater than 45 degrees. The studies which have been made on rudders, which tend to be smaller today than they were in the past. There's a reason for that, of course, is that you have better response to markets with larger container ships and larger loads, and you also have energy savings or better energy use. With respect, a ship with more cargo on it is going to expend less energy per ton transported than several vessels. And if you look at the stern, they're much flatter aft than they used to be. As a conclusion, I'd like to talk about how we can avoid these sort of phenomena. First of all, we can have greater mastery of the weight of the containers, and there are recommendations now which have been set up for this, but they can still be protected. We really have to ensure that we do better on this, because it's far from 100% effective when we see the situation of containers on board during certain inspections. And then we have to look at the position of the containers as well, not just their weight, but their positioning, and we have to reassess these aspects, because sometimes when the containers are loaded, the order of loading and the order of harbors means that they're going to come on board and not necessarily be placed in the best of positions with respect to their weight and their load. So we need to ensure too that stability is sufficient as well. Then there are a number of computers and calculators that have been made available now to compute the parametric rolling, but a lot of times the crews don't really know how to use them. They haven't necessarily received enough training, and sometimes these computers and calculators are really not easy to use. They're not very user-friendly. and they don't necessarily choose the best of routes as well for, and then class marks should enable us to have greater mastery over parametric rolling, thanks to that. This is something that seemed fairly interesting to me, to see the number of ships using these parametric rolling computers. Veritas told me that they developed a class mark in 2019, NR 677, I believe, and the other classification societies are using this. They're creating them using these class marks, but they're not necessarily, they haven't necessarily been adopted yet by ship owners and shippers. So I can refer you to the work that the PSU did with respect to the MSC Zoe, their joint report, with respect to container ships with limits of weight and lashing of loads. For example, in some of the computation standards, we talk about 300 meters with an initial reading of 2.5 meters, but for Zoe, it was 10 meters. But these elements are not necessarily sufficient today. There's some developments and initiatives that France has been proposing or pushing. And in the work with respect to the cargo securing manual, the CCS as well. So I thank you for your attention, and I'll be happy to take any questions if we have time later. Okay, thank you very much for our General Administrator. That was perfect timing, and it was technical, but it was extremely informative, explaining about parametric rolling at sea. It's something that isn't necessarily well known to a number of especially the less experienced ones.